The purposes for this video, focusing on AMA, IMA, and efficiency are, wait for it, what is ideal mechanical advantage, IMA, what is actual mechanical advantage, AMA, what is efficiency, and why aren't real machines completely efficient? So let's dig in. Let's start with our first one, ideal mechanical advantage. Now we've already talked about mechanical advantage, which is kind of that ratio or the relationship between forces or distances. Now we're getting into specific types. Now, ideal mechanical advantage, if you break that down a little bit, ideal means you are dealing with a world that is not consistent with our own, meaning we can call it in a perfect world. So this is never ever actually going to happen. This is like if your object is performing at peak capacity, this is what it would have. So we are not taking things into account like friction or sound or heat loss. Basically, any form of energy that's dipping out, we are not accounting for. And why we like to use this is because we can compare it to, in a moment, the actual mechanical advantage to tell us how efficient our machines are actually working. So to calculate your IMA, you're going to take your DE, which is your distance traveled by the effort force, divided by your DR, which is your distance traveled by the resistance force. Now you need to make sure that both of these are in the same units, so inches and inches, feet and feet, centimeters, whatever, because IMA is unitless. So while we measure things in inches and feet, IMA doesn't have a unit that we use to measure things. And one way I tend to think about this, obviously you'll have your equation sheet, but I think of ideal as a DER. Now again, think about in real life, machines are not fully ideal. If you've ever been on an old janky seesaw, it's not going to run to peak capacity, right? There's rust, there's friction, you get lots of obnoxious sound from that. So it's not going to run at peak capacity like we would like to see. So that's where actual mechanical advantage comes into play, AMA. And this is purely by experimentation. You actually have to build the part, you have to measure the forces to give you what your actual mechanical advantage is going to be. So this is taking in frictional losses, energy losses, and we're still going to compare that with IMA to see how good we're doing. So for AMA, notice how we kind of flip-flopped the numerator and the denominator to a certain extent, but now we're dealing with the forces. So FR is the magnitude of the resistance force divided by FE, which is the magnitude of the effort force. And we're going to be using either pounds or newtons to measure force. Another way you can think about it is FRE, so resistance force, effort force, FRE. Or just use your equation sheet and you're good. Now, before we get to a calculation, let's talk about efficiency. So we can compare AMA and IMA together to figure out how efficient our object is actually working. So percent efficiency is equal to whatever you calculate for your AMA divided by whatever you calculate for your IMA times 100%. And that will come out to be a percentage. Now, keep in mind that no machine is truly 100% efficient. We may have questions where we assume ideal conditions, which means that your efficiency is 100% and your AMA is equal to your IMA. But in real life, that's never actually going to be the case. So let's try out a problem. Let's calculate our IMA, our AMA, and our efficiency for this inclined plane. So this should look familiar from our mechanical advantage video, but there's some information we need to know. So let's pull up our resistance distance, which means we need to move our box from the floor up 32 inches. That's our resistance distance. And our effort distance is how far we're actually pushing that thing up, which is all along that big old slope is 147 inches. So based on that, we can measure, hey, our box is 100 pounds, but I only need 63 pounds to actually push that up. So we've identified our DRs, our FRs, our DEs, and our FEs. So now we're ready for our calculations with IMA. So follow along with me. IMA, I'm going to throw down our equation, is DE over DR. And I'm just going to start plugging some values in with their units. So my effort distance is 147 inches divided by 32 inches. So that tells me my IMA is around 4.59. Cool. Fantastic. Doesn't mean a lot to us right now. Now, our AMA, let's do kind of the same thing, keeping in mind that we're actually using forces to measure this out. So I'm going to write down our equation. AMA is the ratio between your resistance force, which is the box we're trying to lift, versus the effort force, which is the force you're actually putting into that push. So we're going to toss those numbers in. I know that my box weighs 100 pounds. I know I'm only putting in 63 pounds, which is a good advantage. And I find my AMA to be around 1.59. So notice right off the bat, our IMA and our AMA are not equal. In fact, our AMA is less, which is going to happen in real life because IMA and AMA will never equal each other unless we have what we call an ideal situation. So let's do one more step. Let's calculate our efficiency. So if we take our efficiency equation, which is AMA over IMA times 100%, then all we have to do is plop in those numbers. So we have 1.59 divided by 4.59 times 100%, which gives us a final answer of an efficiency of 34.64%.